Great. Good morning, everybody. So this is our third lecture on MOSFETs, and today we're going to talk about PMOS. But before we get into PMOS, I just want to review a little bit what we have done in the last two lectures. We have done the MOSFET statistics, characteristics, and we also have studied the MOS, the current voltage characteristics. That is very important because PMOS, if you look at carefully, it's almost a duplicate of NMOS, except that the directions is from S to D instead of to D to S. So let's give it a summarize of NMOS, that some of the characteristics. Well, first of all, for NMOS circuit symbol, it looks like this, and you have G, you have a D at the top and the source at the bottom. The current through that, either lowercase or capital case, sometimes ID, sometimes ID. So the different symbols, they actually have different meanings. Sometimes we interchangeably use them, but typically D means DC, lowercase d means AC, and I means DC, and I means AC. So just sometimes we possibly use them interchangeably. It's okay. Same thing for voltage. So for MOSFET to be in off state, that we said that VGS is the voltage from gate to from gate to source has to be less than VTN. And VTN is typically like 0.5. And for it's going to be on, or it's going to conduct, VGS has to be larger than VTN. And the difference we call overdrive voltage, VGS minus VTN. And within this mode, we can have either, we look at VDS. If VDS is less than VOV, then it will be in the triode mode. If VDS is, and then in this mode, the kernel ID, the best is probably going to use like ID because this is going to be DC. So we're going to use ID for now. It's going to be Kn prime W times L VGS minus VTN, which is VOV times VDS minus 1/2 VDS squared. So that's in the triode mode. And for VDS larger than VOV, well, VOV is the boundary condition, so you can say either equal sign either way. So in this case, ID will be equal to 1/2 Kn prime WOL times VOV squared. Again, here VOV is going to be just VGS minus VTN. And also here, sometimes it's just Kn equal to Kn prime times WOL. So this equation sometimes interchangeably used. And also we talk about imperfect model. There's a VA, there's a lambda, and with VA equal to 1 over lambda. And we talk about that. And we also talk about the current in the imperfect model. Is this only in the saturation mode? So that ID can be written as 1/2 Kn prime WOL VOV squared plus VDS over RO, that RO equal to VA over ID. Okay, so that's the imperfect model. And the diagrams relation for ID as a function of VDS, and it can be written as this. And each one curve is corresponding to a different VGS. And in the imperfect model, we know that this thing is going to be a little bit slope, and that slope always cross at the third quadrant, and that voltage is what we call VA, or 1 over lambda. Okay. So now we will switch on to our PMOS. The symbol of PMOS is very similar to NMOS, except that the arrow direction is different. And remember, in NMOS, the direction is like this for the NMOS. So this PMOS. And the corresponding symbol for that one, for the middle one for NMOS, is going to be as an arrow pointing down at the source, as a drain source. And the corresponding for NMOS in the last one is on the right hand we draw. As you can see, the difference is that the source and drain are flipped to represent the direction of current that going through S to D. And also the gate voltage now is VSG instead of VGS. Okay. And the voltage is VSD instead of VDS in PMOS, and current is ID. Now we know that ID is equal to IS because IG is equal to 0. There's no current, so therefore you can always use ID instead of I. You can use IS as well. For PMOS, if we summarize the conducting condition, and this is going to be very similar to the NMOS. And the NMOS, we already summarized. We can probably summarize on the next slide to compare them. But over here, I just want to rewrite some of the equations in the table to represent what is the of the triode and the saturation region. So for it to be off, the condition is VSG has to be less than VTP. Now, I want to make sure that VTP here is negative, but VTN is positive. So in order to be comparably write them, we're going to always use absolute value of VTP. So this off state. In on state, VSG will be larger than VTP. But in on state, we can have two conditions. Now we have to compare VSD and VOV. So here we define VOV as a function of VSG minus VTP. So when VSD is less than VOV, it's going to be in the triode region. When VSD is larger than VOV, it's going to be in the saturation region. And in the triode region, the equation for ID is going to be very similar to the one of NMOS. So we can write ID equal to Kp, now it's log ln Kn, multiply width to length ratio, and multiply is that VSG now inside minus VTP with absolute value times VSD minus 1/2 VSD squared. That gives you the current in the triode mode. In the saturation mode, we can write ID as Kp. It's going to be 1/2 Kp times W over L times VOV squared. In the imperfect region, we can write similarly ID equal to 1/2 Kp prime WOL times VOV squared, and then plus VSD over RO. And that RO is what we will define in the next slide. Is this one gives you an illustration of the voltage levels of because VGS has to be larger than VTP in order to be on. Once on, VGS is going to be larger than VTP. We're going to, so VGS is going to be the VOV plus VTP. So that's how much that VGS more than VTP. When VGS exactly as VTP, it's just on the edge between conduction and off. When VGS more than VTP by overdrive voltage, that's why it's called overdrive voltage, VOV, and then the system is start to conduct, but whether it's in triode or whether it's in saturation, it's going to decide on the input, the voltage applied between source and drain on the secondary. So if that drain source and drain voltage is less than VOV, which the top region you can see over here, it's going to be in the triode mode. But if VSD is larger than VOV, and then it's going to be in the saturation region. And now you can apply the equations to calculate the actual current in the device. So this is only for illustration purpose to look at why it works that way or that way. So now I want to get back to compare the NMOS and PMOS just a little bit. So for NMOS, we know that the symbol is going to be, this is the one that we use quite often. We make it a little bigger. So NMOS, PMOS, and here this NMOS. NMOS, yeah, MOSFET. The symbol for this one is going to be G, D, and S. The symbol for PMOS is going to be S, D, and G. For this NMOS to be off, the VGS has to be less than VTN. For PMOS to be off with SG, now you see we are flipping the sign, but we also use absolute value. For its on, it's going to be VGS larger than VTN, and VSG is larger than VTP. Little correction here. And the difference between VGS and VTP is called VOV equal to VSG minus VTP. That's for PMOS. And for NMOS, you have VOV equal to VGS minus VTN. Yeah. So that's the basic conduction, and then the triode and saturation region. So if SG is large, then this is in the saturation region. So it's in saturation region, and the current can be written as ID equal to 1/2 K W L VOV squared, and that ID for the PMOS is going to be also 1/2 KP prime WOL VOV squared. So that's in saturation region. And then if VGS is less than VTN, no, I'm sorry, this is wrong. So this, if it's in the saturation region, which means VDS is larger than VOV, and here is VSD is larger than VOV. Okay, that's in the saturation region. Then in the triode region, we have ID equal to KN WOL VGS minus VTN times VDS minus 1/2 VDS squared. And for the PMOS is going to be one. It's going to be K P prime W over L times V SG minus VTP, which here is absolute value. TP, which is we have to make it absolute value, times VSD minus 1/2 VSD squared. And for this condition to happen, VDS has to be less than VOV, and this is for VSD has to be less than VOV. So that's in the charge region and saturation region. In the imperfection model, we know it's in the only in the saturation. We talk about the infrared model. Then we'll have ID equal to just extra term that we normally use. 1 plus lambda times VDS. And this can be written as Kn W over L VOV squared plus there's R, there's VDS over RO. And similarly, for the PMOS, you can write as well as KP 1/2. Don't forget the 1/2. WOL V squared plus VSD over RO. And we can also draw the equivalent circuit, which, if you remember, for MOS, and for PMOS, and then that equation is ID, which are going to give you MOS. Okay, so now we have this comparison. We can probably move on to talk about PMOS and look at different circuit configurations and try to get the solutions. So this is a video example in a book, and you guys can start looking at the behavior of the device. So let me write down a few variables, and we can go on to the next slide to find the solutions. Well, what this says is that the PMOS has a VTP negative 0.5. So we're going to be take the absolute value, it's 0.5. And we also have VS is 3 volts. So you see the top is 3, the bottom is D, and then the left hand is G. And D is given at 1 volt, which means our VSD is actually given 3 minus 1 is 2 volt. So what we don't know is VG. And VG actually varies between 3 and 0 volts. So the question asking that between 0 and 3, what is the condition of the PMOS, whether it's off, whether it's triode, or whether it is in the saturation region. Now we know that when VG is too small, it is going to be in off region. So what we can conclude from here very simply is that if VSG is less than VTP, it's going to be off, which means, so if VSG is less than 0.5 volts, it's going to be off, right? But the question that if VSG is larger than 0.5, whether it's going to be tried or whether it's going to be in saturation mode. Now we need to use the expression that we have developed on the previous slide, that we need to know that at what condition would it be in tried mode and what condition would it be in saturation mode. Now we know that if we need now to find what is VOV. So VOV is going to be VSG minus VTP. And VSG apparently is Vs minus Vg and minus VTP. And Vs is given as 3 volts, minus VTP is 0.5, and minus Vg, which is equal to 2.5 minus Vg. So from here, we can say that if VOV is less than we need to look at what is VDS. So if VDS is less than VOV, that V is too big, so it's a small one. So if VDS is less than VOV, it's going to be in the trial mode. So for this to happen, we know that VDS, we already found VDS is 2, right? So VDS is 2 volt. So VOV means VOV is going to be larger than 2 volts. It's going to be trial. And VOV equal to 2.5 minus Vg, larger than 2 volts. And we conclude that Vg has to be less than 2.5 minus 0.5. It's going to be like 2 volts. 2.5 minus 2, no, 2.5 minus 2. So minus 2 equal to 0.5. So it means if Vg is less than 0.5, it's going to be in trial mode. But if VDS is larger than VOV, it's going to be in saturation mode. And VDS is 2, larger than VOV is 2.5 minus Vg. So which means we have Vg is we move Vg on this side. So on the left side, so we have Vg equal to or larger equal to 2.5 minus 2 equal to 0.5 volts. So we conclude that if Vg is larger than 0.5, it's going to be in saturation mode. But of course, which has to be less than 3 because the maximum voltage you can have is 3. In fact, 2.5. It's not going to work. So now we have found that the solutions is if Vg is less than 0.5, it's a tri mode. Which is more than 0.5, it's going to be in saturation mode. And from the previous slide, we said if VSG, so here VSG, we said 0.5, right? Now VSG is equal to S minus Vg less than 0.5. So Vg has to be less than Vs minus plus 0.5 minus 0.5. So we found that Vg less than Vs plus 0.5 or minus 0.5, it's going to be 2.5 volts. So between 2.5 volts, if Vg is less than 2.5, it will conduct. Between 2.5 and 3, it's going to be off. So we can write this down. So if Vg is larger than 2.5, it's going to be off. So if Vg is too big, too close to Vs, it's going to be off. So there are 3 conditions now we have found for this particular parameter. So now let's move on. I want to do this exercise 5.7 because you got 6 different questions, the same problem. So I want to go through this together just to understand how this PMOS is going to work. And I also try my best to avoid any mistakes or confusions, because when we get to PMOS, sometimes, always we carry the concept for NMOS. We try to, sometimes we tend to make mistakes. So in this particular problem, some of the numbers given, like VTP is given, which is negative value. So we're going to make it absolute value, 0.5. And Kp prime is given at 100 micron, and WOL is given at 10. So those are the given quantities of this problem. What it wanted you to find out is what VG is going to be in the off region, things like that. Now, in addition to those 3 variables, we also know that Vs is given at 1.8, and Vd is not given, and Vg is not given. So we need to continue to solve for those variables. So let's move on. Since I want just to copy some of the numbers here. So VTP is given at 0.5 volts, and Kp is given at 100 micro, and WOL is given at 10. So these are the given parameters. And so VD was given, VD was not given. What was given was Vs was given at 1.8. Okay. Now, for it to be off, remember we need to one my VSG and VSD. Okay. So for now to be off, so we're going to start with A. Or, in other words, for this PMOS to be on, VSG has to be larger than VTP, absolute value. And we know that VSG is equal to Vs minus Vg, larger than VTP, which is 0.5. So from this equation, we can say that we move Vg on the other side and keep S on this side. So we know that Vg has to be less or equal to Vs minus 0.5. That gives you 1.3 volts. So for it to conduct. But we, of course, we don't know whether this is going to be in trial or whether it's going to be in the off region, whether it's in trial or whether in saturation. So the next question asked is that in terms of Vg, find Vd for which the transistor operates in the trial region. Now we know that in order for this to operate in the trial region, now we need to find VDS, or we also need to find a VTP, VOV. So VOV equal to VSG minus VTP. And so VSG can be written as Vs minus Vg minus VTP. And Vs is given 1.8. So Vs 1.8 minus Vg minus 0.5. So that gives you 1.3 minus Vg. And what it says that this is a VOV. So we are saying that for it to, in trial, we need to have VSD larger than VOV. Now, VSD can be written as Vs minus Vd, and larger than VOV, we've already found is 1.3 minus Vg. So we're going to move, they want you to find Vd as a function of Vg. So we can move Vd onto the other side. It has to be less than equal to Vs plus Vg minus 1.3. And this is Vd has to be less than Vs is 1.8 plus Vg minus 1.3. That gives you Vd less or equal to Vg plus 0.5. So that's in the tried region. And Vd basically talks about what condition it will be in saturation. Of course, we find that already, which means if Vd is larger than or equal to Vg plus 0.5 volts, it's going to be in saturation. You can derive it all the way, but certainly the conclusion will be the same, because what we're doing is SD has to be, no, you know what? I think what we have done was actually, we done it incorrectly. So let me do this in a correct way, actually. So this is C is going to be, this is going to be D in the saturation region. And then this becomes C in the trial region. So in the trial region, the VD has to be. Now, in other words, what we are finding is VSD has to be less than equal to VOV, which means you get a VS minus VD less than 1.3 minus VG. So from here, you have VD has to be large or equal to VG minus plus 0.5 volts, which is the same equation that we derived here, okay? So just make this correction, that C and D that I got flipped. Now we're going to go to E. E asks you, now it's imperfect. It gives you minus 2 minus 0.2 per volt. And from here, we can basically find out, it says we want to find RO. Now, we know that VA equal to 1 over lambda. Again, we're going to use the absolute value. So it's going to be 1 over 0.2, 5 volts. And then we know that RO equal to VA over ID. And I think the ID has to be given. Otherwise, you wouldn't be able to. Oh, actually, no. Come on. Actually, I think what we did was correct symbol. It's confusing about. So C is in saturation. Yeah, we didn't do D at all. So this all C, this is part of C as well. We have to do D first, but we can do D later. But we want to find out what is RO. But RO is from in part D, that ID was given at 50 microamps. So we're going to plug in this number back into 5 divided by 50. That gives you 100 kilo ohms. So that's for E. So now we're going to go back to D. D asks you assume lambda 0. We want to find VOV and VG and corresponding VD. Okay, let me see what I have on the slide. We're going to go to, now we're going to go to D. Okay, so D says that lambda 0 and ID is 50 microamps, and we want to find VOV. We want to find VG, and we want to find VD. Now, since ID is given, and actually it also says in saturation region, that has to be given, otherwise we cannot decide. So once in saturation, we can write ID as 1/2 K prime or Kp prime WOL VOV squared. So VD is 50 micro, go to 1/2 times Kp is 100, W over L is 10 times VOV squared. So we can easily find VOV square root of 2 times 50 divided by 100 and then divided by 10. So that's 0.1. That gives you roughly 0.32 volts. That's VOV. Now we know that VOV equal to VSG minus VTP. And VTP is given 0.5. So we know that VSG will be equal to VOV plus VTP, which is going to be 0.82 volts. VOV is 3. VTP is 0.32. Now, VSG equal to VS minus VG. And VS is given at 1.8 minus VG. So we can say that VG is equal to VSG minus VG is going to be, we move VG on the other side. So we have VG equal to 1.8 minus VSG. VSG is 0.82, so it's 1.8 minus 0.82, that gives you 0.98 milliamps. We found VSG, we found VG. I don't know if I wrote it clearly, so this is VG. Now we want to find VD, because in saturation region, VSD has to be larger than VOV. And this can be written as VS minus VD, larger than VOV. We found is 0.32. So we can find VD has to be less than VS minus 3.2. So VS is 1.8. So it gets 1.48 volts. So that was the number D. Now we already find number E. So now we can go to F, because E says ID is equal to 50. I just want to recap microamps, and lambda is equal to minus 0.2 volts. So we got A. We have VA equal 1 over lambda and equal 5 volts. And we have RO equal to VA over ID. That's 100 kilo ohms. So now we can move on to F. F is given the same condition, which means that lambda is given, so VA is given at 5 volts, and VOV was given 0.32. And they want you to find if VD is 1 volt or if VD is 0 volts. How much would you find for actual ID? That ID initially was given at, I call IDQ is 50 microamps. That's without the channel effect. Now with the channel effect, we can write ID equal to IDQ plus VSD over RO. As similarly here, you can have IDQ plus VSD over RO. And for VSD here, apparently VSD is ID VS minus VD, right? So VS is given, and something in the second equation. And this is 50. That VS is given at 1.8 minus 1 divided by 100. So this gives you 58 microamps. And the second one is 50 plus 1.8 minus 0 divided by RO, which is 100K. That gives you 68 microamps. Now, this is a simplified way to do the variable. You can actually do in a hard way, which means you can always write ID equal to 1/2 kp WOL V squared times 1 plus lambda VSD, and you can plug in VSD because VSD equal to Vs minus Vd, and it has two values, which is 1.8 minus 1 or 1.8 minus 0. This is 1.8, and this is 0.8 here. This is 1.8 volts. So you plug in these two numbers, and you'll find out you'll get exactly the same. For the top one, you get 58 micrograms, and for the bottom one, you get 68 micrograms. And when you look at R, it's going to be 100 kilo ohms. I know I saw this like a problem fairly quickly, but the practice, you guys can rewind and look at it. And also I have posted the solutions, the complete solutions on this slide, so you guys can take a look. And if you have questions, you can always refer back to this to find lecture solution. Since we still have another 30 minutes left, I want to go over a few more examples, probably in a little bit just more detailed steps to solve for this problem. Now, first of all, let's look at problem 5.40. This is one of the homework that was given to you guys. This problem is in fact is exactly the same as the one that we did in the example we did earlier. So what does it say? The problem says that you have a PMOS and you have VGS, we have VG connected at the gate for PMOS. Then you have on the DE side is connect to 0.8 volts. On the S side is connect 2 volts. So over here, and we can mark on that VSG and VSD, and also we can mark the current as ID. So now, from this figure, you can already figure out that VSD is given at 2 volts minus 0.8. That gives you 1.2 volts. And also, VTP was given at 0.4 volts. It didn't give you the numbers like KP and WOL because we don't need them, because we're not solving for the exact current, so therefore we don't need those. So again, looking at recall the three conditions, I'm going to write those three conditions here. So I'm going to do off, I'm going to do trial, I'm going to do saturated. So for off condition, VSG has to be less than VTP. And VSG is equal to, so we're going to write also another section here. So VSG can be written as Vs minus Vg. And Vs is 2, so that's 2 minus Vg. So VSG is 2 minus Vg. And VTP is 0.4. So plugging this one, we got 2 minus Vg less than 0.4. So move Vg on the other side, it says Vg has to be larger than 2 minus 0.4, which means Vg has to be larger than 1.6 volts in order for this to be in the off condition. Okay. Now, once this is larger than once Vg is larger than 1.6, it's going to conduct. Once it's conduct, we have to decide the relation between VSD and VTP and VOV. and VOV. So let's first define VOV is equal to VSG minus VTP. So VSG is 2 minus VG from the previous equation here. So we can write VOV as 2 minus VG minus 0.4. So that's 1.6 minus VG. Okay, we got that one. So now let's look at VSD has to be less than VOV, which means VSD already given as 1.2 has to be less than 1.6 minus VG, which means VG has to be larger than 1.6 minus 1.2 has to be larger than 0.4 volts. So that's going to be the tri-mode. And if it's in the saturation mode, VSD has to be larger than VOV, which means VSD is still 1.2, has to be larger than 1.6 minus VG. So we can derive VG has to be more than 1.6 minus 1.2, which means VG has to be larger than 0.4 volts. So once you get to that point, it didn't ask for current, but you can certainly write down the current ID for each condition. I mean, in the trial region, we can write it as Kp WOL, and you can write as VSG minus VTP, volume squared minus 1/2 VSD squared. And for the saturation region, depending whether it's ideal case or whether it's with channel effect. Without channel effect, we can simply write down as Kp prime WOL times VOV squared. If it is in the considering the channel effect, we can always write as VOV squared and plus VSD ORO. And this, of course, can be written as 1/2 Kp prime WOL VOV squared 1 plus lambda times VSD. So that's this example. I think it's very simple. It's very similar to the one that we did in the video example. But here we just recap from the 3 different relations, whether VSG is larger than VTP, whether VSD is larger than VOV or less than VOV, we determine the 3 different operating regions. Okay. The next example, we're going to come up with 5.27. So let's look at 5.27 is actually MOS. I just want to recap, going back to MOSFET. I'm going to draw the circuit together. So this is going to be very simple MOSFET circuit. You have MOS, you have the source and the gate both grounded, but the gate is grounded, not grounded, it connects to a voltage source VG. And you have the D connected to a 1 volt source, so which means here we have specified that VD is 1 volt and VS is 0. So you can say that VDS is 1 volt. So that is given. What was not given was that VG was given a range, but VT is given. So you can say VT or VT, and sometimes they neglect that N, why it's NMOS, just simply say VT 0.5 volts, and that Kn equal to Kn prime WOL, so that's 1 variable. That is also given as 2 milliamp hours per volt squared. So these are the given conditions, and they want you to find out find ID as a function of VG as VG changes from 0 to 1.8. So we want to find want to find the current ID as a function of VG, and VG is in the range of 0 to 1.8. So VG changes from 0 to 1.8. Now, so apparently when VO is small, it's going to be off, right? So again, we're going to probably look at this 3 different regions. So off. One is off, which means VG now is VGS. So VG is equal to VGS, right? It has to be less than VTN for it to be off. So which means VGS less than 0.5, it's going to be off. And ID is going to be 0. Okay? So, and then we'll look at triode. So in the triode means our VDS has to be less than VOV, and VOV is VG minus VTN, which means VDS has to be less than VG minus 5. So VG has to be larger than VDS plus 5. That's the region. And the current, we can write it. ID is equal to and so that's the current in the charter region. And we know that Kn is given is 2 milli times voltage. Vg is a variable, minus Vtn is given at 0.5. And ds is given 1, so times 1 minus 1/2, 1 squared. And then so this gives you 2 times Vg minus 1. Yeah, 2 times Vg minus 1. So that's what we get for the current in the triode region. And then we're going to go on to the saturation region. In the saturation region, VDS has to be larger than VOV, which means VDS we know that VDS is 1, so we can write down that 1 has to be larger than 1 has to be larger than VG minus 0.5. So VG has to be less than 1.5 volts. And in this case, our ID is equal to 1/2 K N VOV squared. And VOV equal to 1/2 times 2. And VOV is VG minus 0.5 squared. So we got ID equal to just VG minus 0.5 squared. So we can plot this one. So we found in the previous slide, we already find that it depending on VG. So if VG, so there's 3 conditions. VG less than 0.5, ID equal to 0, right? So that's the off condition. In the triode condition that we said that VG is equal to VDS 1, so VG less than 0.5 is a saturation. So if VG is less than 1.5, but larger than 0.5, it's in the saturation. It's off. And the current is equal to VG minus 1 square. And why it's in the VG is larger than 1.5, which is larger than 0.5, it's in the triad mode. And the current is 2 times VG minus 1. So we can plot this one as a function VG as current ID as function VG. So we can derive this into 0, 0.5, 1, 1.5, and 2 volts. So if VG is less than 0.5, I'm going to use a different color. So the current is going to be 0. And between 0.5 and 1.5, it's going to be like a curve. So it's going to be in the saturation region. And between 1.5 and 2, it's going to be in the triad region. It's linear. And you can see here, each of these points is going to be determined, because if you plug in here, which is 0.5, that does give you 0. So you have a continuous waveform. And also one, which is 1.5, basically we can say that if which is 1.5 on the in the saturation region, so it's off region, middle is a saturation region, in the triad region. If which is 1.5, you got 1 milliamp, and you got also 1 milliamp on the equation. So this is the cross point of 1 milli, and this is 2, which minus 1, and this is VG minus 0.5 squared. So we got this problem resolved. Next, I want to do one more example before we conclude. So here we want to look at 5.18. Okay, so we can go to 5.18, either 5.18 or 5.17. Okay, so yeah, 5.18. What was given was that the current ID is 360 microamps. One VGS and VDS is both 1 volt. And also VD would change to 160 microamps, one VGS and VDS equal to 0.8 volts. Now, most importantly, we need to understand what they want you to find out. What is K and what is VT or VTN. We need to know which one equation to use, basically whether it's saturation or whether it's in triad mode. Not because this is going to be in conduct mode because there's current, right? So it cannot be in off mode. But what we needed to know is whether this is saturation or whether in triad mode. Now, how do you do that? Well, we know that we have to find VOV. VOV is VG S minus VTN. And the condition to be saturation mode means that VDS has to be larger than VGS minus VTN, which is same VOV. Now, since VDS equal to VGS in this example, so VDS always larger than, always large. It's just not equal VGS minus VTN because VTN is a number. For example, if VGS is 5 volts, VTN is 0.5, and VDS is also 5, right? So 5 volts is always larger than 5 minus 0.5. So we concluded it's always in saturation. So actually, this is a property we use in the future, is that if we connect gate to drain, it will guarantee that the MOSFET is in saturation. So this is how we do quite a bit in the future, is that we connect, oops. So this is a guaranteed circuit that when D is connected to G, so in this case, VDS is always same as VGS. It's always in saturation. Okay. So now we know it's in saturation, and also lambda has to be neglected. If it's not neglected, it has to be given. Otherwise, you can't solve for the solution. So now, if lambda is neglected, it's in saturation. We can write the equation now. It's going to be 1/2 Kn times VOV squared. Okay. Now we have the condition was given with two different one. So one is that is 360 microamps equal to 1/2 Kn times V, and VOV is VGS minus VTN squared. And the other one is 160 microamps equal to 1/2 Kn times VGS minus VTN. It's the same equation, but so one of them, we're going to just transfer them all the way to here. So one of them is 60 micro, 360 micro times 1/2. So VGS is 1 minus VTN is not given. And the other one is 160 micro equal to 1/2. You look at here, I wrote Kn, not Kn prime, because Kn is equal to Kn prime times WOL. So this equation you guys need to use in the future. So here, we have 0.8 minus VTN squared. So if you look at here, you have two equations. And you also have two variables. The one variable is VTN, the other variable is Kn, right? So we can solve these two variables by simply doing something. But first of all, what we can do is we can use like equation 1 to divide by equation 2. We can eliminate Kn. So let's do that. So if we use equation 1, divide by equation 2, we eliminate the 1/2 and Kn. Then we got this 360 divided by 160, which is the ratio of current. And that's going to be equal to the voltage relations, which is 1 minus, okay, so let me see. It's 1 minus VTN, and then Brandon squared 0.8 minus VTN squared. So from here, we can extend this equation. We can find VTN. So I'm gonna probably not going to go to that detailed, but what you can do is you can multiply, like I know if you guys like in mathematics, you can take a real 0, and what you have is 36 multiplied by 0.8 minus VTN squared equal to 16, and 1 minus VTN squared, because 16 and 36 both have 4 in it. So we'll simply this 9, this 4. So that makes it just a little bit easier. And then we're gonna have here, so 0.64 minus 1.6 VTN plus VTN squared equal to 4 times 1 minus 2 times VTN plus VTN squared. Okay, so it's 9 times 0.64. That gives you 0.576, right? Minus 9 14.4 VTN plus VTN plus 9 VTN squared equal to 4 minus 8 VTN minus 4 VTN squared. So you can see here, what I just want to say is that you can move things around, like you can combine these terms. Okay? So move that on this side. We have 5 VTN squared minus 14.4 minus 8 gives 6.4 VTN. Then minus you have 4 minus 0, so it's, you have 3 point 3.424 equal to 0. You have VTN. The reason I want to also get down to here because you get it 2 different values, right? So you get minus, which is 6.4 plus minus square root of 6.4 squared. Use the quadratic equation. Minus 4 times a times 4 to 4, because it's minus sign, so it becomes plus, and divide by 2 times 5. So that gives you 2 values. Basically, only one of the value is going to be valid because one of the value is going to be incorrect. So once you get this 2 different values, I don't know what exactly what is going to be, but one of them is correct, the other one's incorrect. And then plugging VTN to that equation, any equation like this 360 equal to 1/2 K N times 1 minus VTN squared. You plug in this VTN, you can get Kn equal to 2 times 360 divided by 1 minus VTN squared. And the solutions are actually available in this postcase. The numerical value is not so important here. The most important thing is that to understand how to solve for this problem. So I think here we basically covered both NMOS and PMOS, and we covered the different operation regions. We covered the imperfections and so on. I want to summarize a little bit before we conclude. But in next lecture, starting next, we're going to spend 3 lectures on the DC operation of 2.5 lectures on in the future. But here, I just want to summarize a little bit on the MOSFET conduction. Can we do this again? So if you look at NMOS and we look at PMOS, guys, take note is that in off region means VGS less than VTN, and this VSG is less than VTP. Okay, so this is the difference. And in the triad region, we have VDS is less than VOV, and of course VOV is defined as VGS minus VTN. That's difference between voltage, the overdrive voltage. And here we always define as VSG minus absolute value of VTP. That's how it's defined. And in the trial region, SD has to be larger than, has to be less in the trial mode. To less than VOV absolute value. In the saturation region, VDS has to be larger than VOV, and ST has to be larger than VOV. And for the current condition in the trial mode, let me write down here. So in the trial mode, ID equal to Kn prime WOL VGS minus VTN VDS minus 1/2 VDS squared. And let me actually move this saturation down a little bit so that we get a better picture. So this in the saturation in the region for PMOS, it's going to be Kp prime WL. We SG, remember this is always opposite. VT P absolute value. We SD always opposite minus 1/2 we SD squared. That's in the trial region. Just want to mark this down. In the saturation region, you have VDS larger than VOV, and the current ID is equal to Kn 1/2 Kn prime WOL VOV squared. And here you have ID is equal to Kp WOL, also 1/2. Don't forget that 1/2. In terms of equivalent circuit, that's a symbol, and the equivalent circuit has, depending on whether you consider the perfect situation or non-perfect, you have an equivalent circuit of, in the perfect situation, you have VDS in relation to VGS, and you have ID equal to 1/2 K times WOL VOV squared. And similarly for the PMOS, you have VSG, you have current, and you have ID. Here is ID, and you have also ID equal to Kp WOL. WOL is 1/2. So that's in a perfect model. In an imperfect condition, we can write ID to 1/2. We can write as Kn prime WOL VOV squared times 1 plus lambda VDS, or it can be written as okay. That equation for PMOS is going to be very similar. The only difference is we SDORO instead of VDS, right? The equivalent circuit is going to be also very similar. And the only that the right hand is going to be SD instead of the right hand is, the left hand is going to be VSG. But in other diagram, we have VDS. Both RO is going to be same, I is going to be the same. That's what we have. So you guys need to write this down many times so that you can get really proficient in terms of recording equations, determine which region, and get the solution and so on. But the idea is that we're going to continue on. As I said, next lecture, we're going to do multiple examples so that you guys get really familiar. We're going to also do the DC biasing in a number of different operations. So here, we're going to stop. I'll let you guys come to my office hours. It will be online. So have any questions, we're going to try to address any question you might have. But otherwise, we'll see you next time. Bye.